So dear students, today we will start a topic, stream function and its significance. In this topic, we will learn how the stream function is introduced, what are its properties, what is its significance, and what is the relation with velocity components in terms of polar coordinates, and naturally some examples. So first of all, if we look at the highlights of this topic, the first thing is that this is the function, this is a scalar function which exists for incompressible type of flows, and I'm talking about the two-dimensional flows. So for two-dimensional flows, this function is constant along the corresponding stream lines. And then the next is that it exists for both rotational and irrotational flows, which we'll prove later. And if the flow is irrotational type of flow, then it becomes a harmonic function. That means the Laplace equation is satisfied. And then we'll show that if there are two flow lines, and then there will exist naturally stream function on the two lines, and the difference of the values of stream function along those two lines will represent the flow across a curve joining the two streamlines. So this is a property, or you can say this is the physical significance of a stream function. And also we will represent the polar velocity in polar coordinates in terms of stream functions. So first of all, if I talk about the existence of a stream function, then we'll consider the incompressible flow, two-dimensional incompressible flow. So first of all, if I consider two-dimensional incompressible flow, then I'll consider the equation of continuity for it, which is the mass conservation equation, mathematical expression of mass conservation equation, or this is also called the divergence free equation. So for two-dimensional incompressible flow, equation of continuity is divergence of q is 0, where q is the velocity, or you can write it delta u delta x, delta v delta y, delta w delta z, where naturally u v w are the velocity components in x, y and z direction. So since I am considering only the two-dimensional flow, and this is in 3 dimension, so I convert it into two-dimensional equation of continuity, which converts to delta u delta x plus delta v delta y is equal to 0. It is for two-dimensional. I have considered only two directions, x and y. Now, if I talk about the equation of streamline, for two-dimensional flow, where I say nothing, or I do not restrict myself to the rotational flow or the irrotational flow. I am talking about all type of flows. Just the condition is that I am taking the streamline for two-dimensional flow. For that, equation is dx upon u is dy upon v. This is the equation of streamline. I may also write it as this equation 3 may also be written as u dy minus v dx is equal to 0. or I may also write it as minus u dy plus v dx is equal to 0. So this is a differential equation which will become an exact differential equation if certain condition is satisfied on u and v. And what is that condition? Now 4 is exact if I say v to be m and u to be n, then I'll say that this is true if delta delta y of v is equal to minus delta delta x of u. As I said you earlier, that v and u are m and n, and for 4 to be exact, this type of condition should be satisfied. Or delta u delta x plus delta v delta y should be 0. And if you look at 2, in case of two-dimensional incompressible flow, this type of equation exists, which is nothing but the flow equation, flow existence equation. So if I look at 2, I say that this is true if flow is incompressible. So if it is existing, the condition for the exactness is existing, I'll introduce a function. I'll introduce a function which is helping to make 4 to be exact. So this implies that 4 is exact. And since it is exact, it simply means there exists a function such that the total derivative of that function is equal to the left hand side of equation 4. 4 is exact implies there 4 means the left hand side of 4. There exists a function, say I give the name to this function, say psi, which is a scalar function, such that minus u dy plus v dx, which is left hand side of equation 4, is equal to d psi. Naturally, psi is a function of x and y, so I may write this psi as delta psi delta x dx delta psi delta y dy. And comparing, I get u is minus delta psi delta y and v is delta psi delta x. I may also take u is delta psi delta y and v is equal to minus delta psi delta x, because in the previous sheet I have manipulated this equation, the expression of equation 3. So I may use either this or this, but I have to take one trend for mathematical simplifications or for theory. So these are the you can say this is the relation of Cartesian velocity components and a function psi. This function psi, which I have introduced here, psi, is called the stream function. And this is 5. 5 is relation between velocity components and function psi. And the psi function is called stream function. So in this way, I have introduced a function which is a very helpful function in fluid dynamics for the analysis of the flow problems. And another thing which I may prove from here is that I have defined the left hand side of 4 This is the left hand side. This is from this equation 4. I have picked the left hand side, and now at the right hand side it is equal to 0. So I may say that along this line d psi is 0. From 4, this is another part, d psi is 0, because look at this equation. From 4 the left hand side is 0, and therefore the right hand side is also 0, which implies psi is equal to constant. Since the streamlines are the flow lines, I get a result that along a streamline, a stream function may be introduced such that it is constant there. So along a streamline, the corresponding stream function is constant. This is very important result, right? Now, if I talk about the three-dimensional flow, then it is not necessary that stream function is constant along a streamline. There are certain conditions which are necessarily to be held for a stream function to be constant. And at this place, I am talking about the two-dimensional stream function for the two-dimensional flow. So here your stream function is constant along the stream line. Now, because this stream function or this function is introduced with the help of a streamline, that is why its name is a stream function. You have considered a streamline, you find the condition of exactness, and which is true with the help of equation of continuity, and you get psi. You have introduced psi. So this psi is called the stream function as it is introduced with the help of a streamline. We can also say in a converse way that if a line along which a stream function is constant is called a streamline. ये भी हम कह सकते हैं कि there is a line along which there is a stream function, which function is constant, then that line is called a stream line. Now next, I consider the property. Second property, this is the first property. Now I come to the second property, and the property says that for third property is next property. For irrotational flow, stream function is a harmonic function, that is, a stream function satisfies the Laplace equation. So in case of irrotational flow, your stream function is harmonic function. If you look at the introduction of stream function, in the whole analysis, I do not restrict myself for the irrotational or the rotational flow. I just consider the equation of continuity for the incompressible flow, and I attain a function which is called a stream function. It simply means that stream function exists for both rotational as well as irrotational flow, which is a very important property regarding the stream function, because in the coming lectures you will be introduced with the potential function, which is a function which exists for some particular type of flows. But stream function exists for incompressible flows, but the flow may be either rotational or irrotational. So it's one of the properties that stream function exists for both rotational and irrotational flow. But if the flow is irrotational, then stream function satisfies the Laplace equation. So first of all, the important thing is that stream function exists for both rotational as well as irrotational flows. Rotational as well as irrotational flows, right? Now I come to my basic property that for irrotational flow, the stream function satisfies the Laplace equation. Actually, for irrotational flow, the curl of Q is 0. And if I find the values of the components of rotational flow, then from curl of Q, I can get that curl of Q is equal to actually rotational uh, about the omega, which is representing the rotational velocity. It is represented by half of curl of Q. So if I open this half of curl of Q, I'll get half of I delta W delta Y minus delta V delta Z plus half of J delta U delta Z delta W delta X plus half of K delta V delta X minus delta U delta Y. But since I am considering only the two-dimensional flow, automatically this component will be 0, this component will be 0, because here W is 0, here Z is not considered. In this case, Z is not considered and W is already 0. So we are just left with this third component. So in case of irrotational flow, of two-dimensional flow problem, for two-dimensional flow, omega is just half k w v w x minus w u delta y, derivative of u with respect to y. And if the flow is irrotational, curl of q has to be 0. For curl of q to be 0, half of delta v delta x minus delta u delta y should be 0. Now if I put the values of v and u in terms of stream function, I have defined the values of u and v by 5. U is minus delta psi delta x and v is my delta psi delta u is minus delta psi delta y and v is delta psi delta x. I just put these values here, these values in 6. Yes, it is 6. So using 4, using 5, using 5, I get delta, I take in the left hand side. In left hand side of 6, half of delta delta x v. V was delta psi delta x. Delta psi delta x minus delta delta y minus delta psi delta y. Oh, in this case I may take the complete equation 6. So I write using 5 in 6, right? Then this is equal to 0, or delta 2 psi delta x2 plus delta 2 psi delta y2 is 0, which is nothing but the Laplace equation. So Laplace equation is satisfied, and we know that if Laplace equation is satisfied, then function is called the harmonic function. So psi is a harmonic function, but we have to keep in mind that psi is a Laplace function only for irrotational, right? If I talk about a simple example, that I have given some velocity and it is said that define if we are given some stream function and we are set to define the velocity, then it is very simple. Suppose we are given psi is equal to x cube y square, and we are set to find the velocity functions, velocity components. Then I know that u is, I have taken u is equal to minus delta psi delta y. U is minus delta psi delta y. So it is equal to minus twice x cube y. This is just the u. And v is delta psi delta x, which will become 3x square y square. If we have certain doubt that whether it is correct or not, we can put u and v in the equation of continuity, and from there we'll find that if equation of continuity is satisfied, our calculation is correct. So this is the way to find u and v, and from here I can define my q. This is minus 2x cube yi plus 3x square y square g. This is your velocity. So from here you were asked to find velocity. So this is a very simple calculation to find the velocity, right? Now, if I talk about the importance or the physical meaning of this stream function, for that I would like to give a visualization of it. First of all, physical significance with the help of an example. Suppose I know that my u is minus delta psi delta y and v is delta psi delta x, right? Suppose I have given some velocity u is equal to minus twice x square y. Suppose I am given this type of velocity component u. Now I would find the value of u at different points of streamlines. Suppose I have one streamline like this and one streamline like this. On this streamline, suppose this is first streamline and this is second streamline, and on the between these streamlines, suppose I take this cross section. At this cross section, let it be y is equal to 1, let it be y is equal to 2, y is equal to 3. Likewise, I can take more values, and let at this point x is taken as 2. Similarly, let at this point I take x is equal to 3, and naturally corresponding to x is equal to 3, there will be the values of y. Now, if I find what is u1, what is the velocity u1 at what point? At 2,1. u1 at 2,1. Naturally, I get minus 8. If u2 at 2,2, I'll get minus 16, and u3 at 2,3, it will be minus 24. So it is from right to left because you are getting velocity in negative symbols. So you see that velocity at different points is different. Similarly, if I find the velocities at x is equal to 3 corresponding to y is equal to 1, 2, 3, I'll get some other values. So if the values of the velocities are different at different points of this cross section, and we know by mass conservation law that mass has to be remained conserved. It simply means that there should be some law, some mechanism to conserve them. U is different. At point 21 it is -8, at 22 it is -16, at 23 it is -24. But I have to stick with the mass conservation law as well. So it simply means that as we move from one streamline to another streamline, because naturally there will be streamlines like this. These are the streamlines because streamlines are parallel to each other. So as I move from one streamline to another streamline, naturally there will be, because discharge is changing as the value of velocity is changing, simply means that the discharge is changing. So it simply means that there should be a relation between the distance and distance between the two streamlines and the discharge through the cross section joining the lines, right? And it will be happened if there is certain function, which function will give you some information about the discharge. As I said that since the velocity is changing from streamline to streamline, and it is depending upon the distance between the streamlines. So if I join one streamline to the another streamline, naturally there should be some function representing the flux, representing the discharge, and that function is nothing but the stream function. So this implies there exists certain relationship between flux, or you can say discharge, and space coordinates, or you can say the positions on the streamlines, right? This implies there exists certain function representing this relation, and we call this function as the stream function. The function is nothing but stream function. So I have introduced some stream function with the help of a very simple visualization, a very simple example. Suppose I consider a cross section with the help of a parallelogram. Suppose I consider a parallelogram, and in this parallelogram I take a cross section like this. This is a cross section which I say P, Q, R, S. And if I take this direction to be X, this direction to be Y, and this direction to be Z. Then if I talk about the discharge, you take this point as 1 and this point as 2. Alright? So let u be the velocity in x direction, and I take a very small portion of it. Then this portion is dy, a small cross section. If u is the velocity in x direction and q is discharge through PQRS, this small portion, this PQRS, in x direction, then what will happen? This the small discharge dq, or you can say at discharge at a point, discharge, it is the infinitesimal discharge through PQRS. It will be u dy and 1. What is 1? 1 is the unit distance in the direction of z. So dy dot 1 or dy multiplied by 1 is representing the area through which we are taking the discharge. So what we do when we take the discharge, we just multiply the velocity in the direction of discharge into the surface area. So it is dy into 1. So this is u dy. And if I want to take the discharge from point 1 to 2, I integrate u dy from 1 to 2. And as I know that u is taken as 2x square y in my example, so this implies, so I take it 1. So q, if I denote it by q from point 1 to 2, then q is equal to 1 to 2. U means twice x square y dy, which means x square y square from 1 to 2. Now what is this x square y square? This x square y square is the function which I have introduced, that there should exist a function giving you the relation between the flux and the value of stream functions, right? ये flux है, this is flux, and this is the difference of value of some function. What is that function? Let psi is equal to x square y square. Then 2 implies that q, that is flux across PQRS, is equal to psi 2 minus psi 1. What is this psi 2 minus psi 1? Psi 2 is psi 2. You see, this is 1 and this is 2. So psi 2 minus psi 1 is nothing but the difference of the stream function at PQ and SR. So it is difference of stream function at 2 and 1, right? So discharge, Q means the discharge through a cross section between PQ and SR, and this is equal to the difference of stream function at the two lines. So this is the physical significance, and this physical significance is shown with the help of a physical example. You can see here that in this case, when I take u is equal to minus 2x square y, you get a stream function like x square y square. So if I talk about this is in x direction, right, which I have used, it is in x direction. If I talk about the value of stream function in y direction, or you can say if I define psi u, psi u is stream, psi u is representing its relation with the flux in x direction. If I take psi v, it is the flux, it is giving you the relation of stream function with the flux in y direction, right? But if I take the concept of control volume, that mass conservation law says for two-dimensional flow that whatever be the flux in the x direction and whatever be the flux in y direction, the both should be in equilibrium, like the sum of the two fluxes should be 0. So in that case, what I get, psi u plus psi v is equal to 0, or psi u is equal to minus psi v, right? So it simply means that volume flow rate or flux, volume flow rate in x direction is equal to, or if volume flow rate in x direction is given, you can find it for the y direction. So volume flow rate in x direction is equal to negative of the volume flow rate in y direction. So with the help of one, you can find the another one. This is another property. So if I say that u is equal to minus delta psi delta y and v is equal to delta psi delta x, I may write it vice versa. U is equal to delta psi delta x and v is equal to, this is y, v is equal to minus delta psi delta x, right? Now I come to the mathematical expression or the theoretical expression for the physical significance of stream function. This I have told you with the help of a mathematical example, and now I would like to express you the same relation with the help of a with the help of theory. So for that, I'll consider a situation like this. You consider two streamlines, and then as these are the streamlines, suppose this is the first streamline, this is the second streamline, naturally there will be flow like this because streamlines are always parallel, right? Here I consider a cross section such that if I talk about the normal unit vector, then along this normal there is the unit vector n along this normal, and let q be the velocity component. So naturally q dot n will give you the velocity along the normal, or you can say velocity of the flux, right? Here you consider a point. At this point I take I call the surface area of this as ds, and so I may consider x direction, a length in x direction and length in y direction. Suppose this is x direction and this is y direction, and accordingly let it be dx, let it be dy, and let it be ds, right? In x direction I have a velocity component u at a point of ds and a velocity component v in the direction of y, in such a way that if this angle is theta, then naturally there will be two directions, one along n. I'll mark it later. Now look at this. I consider a strong cross section. Consider a cross section between two streamlines. One and two. The cross sectional area is ds, right? Now what is Qn? It is flux velocity in normal direction to ds. Why? Because n is along the normal to ds, right? So what I take, I want to find what is q dot n. I take q dot n is equal to, it simply means I have to resolve u and v in the normal direction. That means I have to resolve this u in the direction of this normal, in the direction of this. Similarly, like this. Similarly, I have to resolve this v in the direction of, again in the direction of normal, right? So if you resolve these, you will get u cos theta, because it will make angle theta. You will make angle theta with, this is angle theta with x direction. And if you look at v, it will make theta will invert normal direction. So it will be, sorry, it is not cos theta, it is cos, it will become, this is theta, so this will become 90 minus theta, right? So it is cos u cos 90 minus theta. And if you look at the angle made by v with inward normal direction, then it is theta, and since it is in inward direction, it will be minus v cos theta. So it is u sin theta minus v cos theta. If I write u and v in terms of psi, minus delta psi delta y sin theta minus delta psi delta x cos theta. I may write it as minus delta psi delta yi plus delta psi delta x j. Here it is sin theta I minus cos theta j. So if I compare the two sides, what is my n? N is a vector, naturally it is a vector, sin theta I minus cos theta j. I may write this sin theta and cos theta in terms of ds, dx and dy. So I write it as dy dsi dx dsj with the help of the triangle. So using this, I will get q dot n is equal to minus delta psi delta y dy ds minus delta psi delta x dx ds. Okay. Now I want to find the flux across this whole cross section. So what will be the flux? Flux will be q dot n from 1 to 2. So it is minus delta psi delta y dy ds delta psi delta x dx ds for the cross section 1 to 2 for surface ds. And I can write it as derivative of psi. You may solve it and get that this is nothing but psi, which means this is psi 1 minus psi 2. Again the same result, that flux across a cross section joining the two streamlines is nothing but the difference in the values of stream functions at the two lines. So this is the result, that flux across a cross section, this cross section may be a curve, flux across a cross section is equal to difference of stream functions joining the stream functions at the two flow lines or streamlines flow lines which provide the cross section. So this result is very important. Whenever you know the value of stream function at the two streamlines, you can easily find the flux or whatever is the amount of the fluid which is passing through the cross section, adding the two streamlines, joining the two streamlines. So this is the importance of this stream function. Now with the help of given velocity components, you can find the streamlines, and with the help of stream function, and with the help of stream function you can find the velocity components. For example, if I'm given with some velocity with some psi. Suppose I am given psi is equal to x square minus y square, and I am set to find the velocity components. In the previous example, we were given u and v, and we were to find psi. Now here we are given, uh, sorry, with the in that example also we were given psi, and we were to find u and v. Similarly, there may be vice versa. That means you are given u and v, and you may find psi as well. So if psi is given, you may be asked velocity. You may be asked velocity at some particular point. You may be asked to draw the streamlines, and you may be asked to find the direction of flow. For example, in this case, if u is to find, then u is minus delta psi delta y, and so this is only 2y. If you are asked v, this is delta psi delta x, which is 2x. This is the first part. Now, if you are asked uv to find at some particular points, say 2, 1, you can easily find u will be 2 and v will be 4. So, your velocity is 2, 4 at this point, right? Um, if u is taken as delta psi delta y and v is taken as minus delta psi delta x, then you will get some another type of result. Like you will get u is equal to uh, minus twice y, and v is equal to minus twice x, and in that case your uv at 2, 1 will be, यहाँ पर एक mistake हो गई है, this is 4, this is 4, so it is 4, 4, while it is minus 4, minus 4. So this is nothing but, in one case you are having the flow from right to left, and in the another case you are having the flow from left to right. So quantitatively there is no difference. Qualitatively it is flow from left to right or right to left, right? Now if you are asked what is the resultant velocity, so resultant velocity will be is square root of u square plus v square. So naturally it is 4 square plus 4 square, or 4 2. It is the resultant velocity, and whatever will be the units, right? If slope of a streamline is asked, again you can give the slope of streamline. Slope of a streamline will be v upon u, or this is v upon u means 2x upon 2y. So it is x upon y. It may be asked at different points. Suppose it is to be asked at 2 1. यहाँ पर मैंने 1 लिख दिया. It is 2 2 होना चाहिए. नहीं तो ये गलत दे रहा है रिजल्ट. It is 2 2 2 2. It is also at 2 2. So this is 1. It is the slope of a streamline. आप यहाँ से निकाल सकते हैं slope of streamline, because in the equation of streamline you were having v and u, right? And if you are asked to draw the streamlines, like from this example, draw the streamlines, then what we will do, we know that d psi is equal to constant along a streamline. So it simply means that from the given question I may write x square minus y square is equal to constant, and let this constant be c. Now for c is equal to 1, I get one streamline, x square minus y square is 1. For c is equal to 2, I get x square minus y square is equal to 2. And similarly, giving different values to c, I'll get the streamlines. And initially I said that streamlines are parallel to each other. So what type of streamlines I get? Suppose this is for psi is equal to 1. This will be for psi is equal to 2. This will be for psi is equal to 3. So these types of streamlines will be sketched. Right? So this is the draw of streamlines. So suppose I get a streamline x square plus y square is equal to c square. Then naturally, by giving the values to c as 1, 2, 3, etc., I'll get the circles, which will be the concentric circles. So streamlines are in the form of circles, which are concentric circles having the different radius but the same center. So it is also interpreting that streamlines are parallel streamlines, and which can be found with the help of d psi is equal to constant. So in the next lecture, I'll continue the properties of streamlines and the relation of streamline with the polar coordinates. Thank you.